Hello everyone, we're looking at question number 2 of winter 2016 paper 4-3-9702. The question reads, an ideal gas initially has pressure 1 into 10 raised to the power of 5 pascals, volume 4 into 10 raised to the power minus 4 meter cube, and temperature 300 Kelvin as illustrated in figure 2.1. So we have the initial state and then we have the final state. The pressure is changing, the volume isn't changing, and then we have the temperature. A change in energy of the gas of 240 joules results in an increase in pressure to a final value of 5 into 10 raised to the power 5, which means that energy was given and which resulted in this final state. A part reads, calculate the temperature T. The easy way to approach this question is to see the relation between pressure, volume, and temperature. Now, we know that pressure is directly proportional to temperature. When we say that pressure is directly proportional to temperature, when volume is constant. Every time we say something is proportional to something, there has to be a third quantity that is being kept constant. Only then you can say that something is proportional to the other thing. So I'm saying that pressure is proportional, directly proportional to temperature when the volume is constant. And with that we can derive the formula P1 over T1 is equals to P2 divided by T2. The reason why I'm saying this is because if we were to write pressure, volume, and temperature in one equation, we will be seeing that pressure is directly proportional to temperature and pressure is inversely proportional to the volume. And I can also say that pressure is inversely proportional to volume when temperature is constant. And from that we can deduce P1 V1 is equals to P2 V2. P1 V1 is equals to P2 V2. And we can also say that volume is directly proportional to temperature when pressure is constant. And from that we can say V1 over T1 one thing we need to understand that every time we say two things are proportional to each other, directly proportional to each other, they have to be written as fractions. Because if I say P1 over T1, which means that they're directly proportional. If I'm multiplying two things, that means they are inversely proportional. Now, if we look at this, we can see that the volume is remaining constant. When the volume is remaining constant, where can we get that? Yes, pressure is directly proportional to temperature when volume is constant. I can use this formula then. Then simply you have to write pressure 1, we can assume this as pressure 1. So we will write 1 into 10 raised to the power 5 divided by temperature 1, which is 300 Kelvin, and that is going to equal to pressure 2, which is 5 into 10 raised to the power 5 divided by capital T. Now all you have to do is simply cross multiply. When you cross multiply, you have 300 into 5 into 10 raised to the power 5 the answer you should be getting by cross multiplying is 1500 Kelvin, and that is your answer here. Moving on towards the second part, the amount of gas. If I go back to the question here clearly says that it's an ideal gas, which means I can use the formula PV is equals to nRT. PV equals nRT. And we have to find the amount of gas, which is N. You can use information either from this or this, it depends on you, but I would say that you go for the initial state, because you can only use this if you're sure that your answer is correct. If this answer gets wrong, then your other part will get wrong as well, so it's best that we go for the initial state. For that, we have the pressure as 1 into 10 raised to the power 5 1 into 10 raised to the power 5 multiplied by the volume, which is 4 into 10 raised to the power minus 4. You have to ensure that the units are right as well. It has to be in meter cube. That has to be in pascals. N into our constant, which is 8.31, into temperature, which is given to us as 300 Kelvin. And you just put this in calculator. 1 into 10 raised to the power 5 multiplied by 4 into 10 raised to the power minus 4. I divide this by 8.31 multiplied by 300, and you get 0.016 moles as your answer. Moving on towards the B part, which says the increase in internal energy of a system may be represented by the expression. State what is meant by the symbol this and this. Okay. So we know that this represents the internal energy given to us. Q represents the thermal energy, and this represents the work done. Now, you can see they have given us this positive sign here. They could be negative as well. One thing that we need to understand is that when it's positive, this means that the thermal energy / the heat energy is supplied to the system. The thermal energy is supplied to the system. This 2 here is extremely important, and this positive W, which is the work done, represents that the work is done on the system. The work is done on the system. This 2 and this on is extremely important. important. However, if they had given us negative Q, this would have meant that the heat energy is released from the system, and if they had given us negative W, this would have meant the work is done by the system. So this is it for our answers as well. If you had written thermal energy and work done, that wouldn't have been as strong as writing thermal energy is supplied to the system, work is done on the system. Now we have the second part. State for the gas in A the value of this, and this. They have given us the equation, how these three are related. Okay, let's look at these two first, because once these two are solved, you can automatically find the internal energy. Let's look at the thermal energy. We go up and the question says a change in energy of the gas of 240 joules. Positive 240 joules of thermal energy is supplied. That is our answer. 240 joules. They've written it above that 240 joules of thermal energy is supplied, which means 240 joules. Let's look at the work done. When it comes to ideal gases, the formula of work is pressure into delta V. The reason why I have written delta in caps lock is because it's extremely important. Delta V is change in volume. Unless and until there is no change in volume, you will say that work done is 0. No matter what the value of P is, no matter how much P is changing, if V is constant, if the volume is not changing, your work done will be 0. When you go up, you can see I have highlighted this as well, that the volume remains constant. Now we know that the volume remains constant, there is no change in volume. We will say that the work done is 0, and so our value should be 0. And now once we're done with these two, you'll see how easy this gets. We can see the equation that's connecting all these three is this. We have 240 plus 0, and that simply gives us the answer 240, and that is it for the change in internal energy. And this is it for this question as well.